Okay, 1 and 2, very straightforward. Dot product should be 18 plus 45, so 63 for number 1. 6 plus -10 should be -4 for number 2. Um, guys, we talk. Thank you. For 3 and 4, fortunately, each vector originates from 0, 0. So the coordinates you see are the actual vector components. That's actually 8, 4, and -9. Those are actually that three vectors. They just originate in origin. So if you want to find a between those two vectors, you want the dot product first, then find magnitudes, and then do the inverse cosine, right? So for example, for number 3, should be very straightforward. Like, okay, well, I know at vector 8, 4, dot product with vector dot product with vector -7, -9. So that'll be -56 plus -36, which of course is -92. After that, and it's gonna be a really wide angle, obviously, right? So -92 equals the magnitudes of each. What the magnitudes are gonna be what? Um, root 80 and root what is it, root 130? Oh, not the angle between them. Oh, then never mind. Let's go on to a different one. Thanks. Okay, let's do this one here. All right, so for here, yeah, if you want to find that angle, my apologies. That should be a dot product -16 plus -2, so you get -18. -18 equals the magnitudes, which is root 8 times root 65, I think, times cosine theta. So theta is the inverse cosine of all that junk, right? Yeah, let's work that out. Inverse cosine of that. You guys are 142.13 degrees. Yeah, so you guys should be okay with that. Okay, that's good. Okay, cool. I think 8, 9, 10 should have been fine as well. If you're cool, 7. And how are you guys with number 11 or 12?
Wait, the final answer for those two expressed in this vectors.
Yeah. Right.
I wouldn't be given the formula. I'd find.
Yeah. Yeah, the formula, if you do it, will be the dot product over the magnitude of, so you're projecting u onto v. So if you square the magnitude of v, you should get that. And then times vector v. So if you clean it up, you should get -62 or 58. What does that reduce to? Right. So when you're doing a projection, essentially what you're doing is this. You're taking vector u, you're putting one of its components as a projection on the v, meaning we scale down v to its unit vector. So vector v gets scaled down to its unit vector. What's the magnitude of a unit vector? 1, right? So you scale it. So that's why we're doing vector v divided by its magnitude. And when you scale it down, then we want to scale it back up afterwards. How do I scale it back up? I scale it back up by doing the dot product of this divided by the magnitude of v. Why does that make sense? I'm going to walk you guys through that derivation again because I think I didn't explain it all the best I could yesterday. Right. So yeah, I'll explain that again for you guys. But at least the calculation wise, you guys are cool. Just playing the formula and working it out. Okay. All right, then let's move on to the notes. Here we go. So let me explain dot product one more time, like the derivation behind it, because I think kind of not explain it the best as I could. So, and by the way, I will put this as an extra credit question on our test when we come back from break. This will be an extra credit question. So if you want to,
That deviation.
yeah, I'll say driving from starting with this, drive that point. So how do I drive? So you have vector A and B, right? So they're going that direction. But when you want vector A minus vector B, what do I do about vector B? Because right now it's pointing this way, right?
You need the negative.
Yeah, I want the negative, right? So I want to reverse it. So if I reverse it, it would actually look like this. So if I redraw that coordinate plane, and let's use different colors, use green. That's negative vector B, right? So of course, this right here is positive vector A. So if I add those two vectors, how do I add vectors geometrically? You connect the tail of one vector to the head of the other, like that. So that's negative B plus A. Well, if you think about it, yeah, you're just adding those two vectors, right? So there we go. That's the same thing as A minus B. And then when you look at what's our goal? Our goal is to solve that angle, right? What law did you guys learn last year? So advanced class, that allowed you to relate these three sides and that angle. Log cosine. Perfect. What's log cosine? Let's see. This square equals that square plus that square minus 2ab cosine theta. That's exactly what's happening. The minus 2ab cosine theta, that's where that's where that's like the c side opposite theta. Okay, so then this is the one part I wasn't really sure about. And now I'm more sure about it. Whenever you do a dot product of itself, it's going to wind up becoming the magnitude squared. And the reason why that's true, if you come with a hypothetical vector, like say 1, 2, and you dot it with itself, what's the dot product for that? 5, right? And if we think about it, the magnitude of that vector on its own is what? And if you square root 5, of course you get 5. So the dot product is the same thing as that. That's a little side note. It's like a property of vectors that we just accept. But we see why it works when you come with hypothetical scenarios. So this right here is essentially dotting it with itself. Now, when you dot vectors in this manner, like A minus B dot A minus B, it's kind of like a foiling process. You do A dot A, negative A dot B, negative A dot B, and plus B dot B. Fine. A dot A is that, B dot B is that, and of course you got two of these guys. So all in all, this right here is that. And what do I do with that? I substitute. I replace this with that junk. By doing that, what happens afterwards? A bunch of things cancel, right? A bunch of things cancel. What cancels? A squared and B squared. And of course, the twos will cancel once the A squared and B squared are gone. So we're stuck with the dot product of AB equals that expression. And that enables us to solve for the angle between the two sides or the two vectors. So that's where it comes from. Of course, I'll give you that relationship. That'll be there. So that relationship will be there. We can use that to solve for the angle between two vectors. So we're okay with that now. Does that make sense? Comfortable? Okay. Then the projection part. This part's a little confusing. I don't think I explained it the best I could. So we deliberately made vector v horizontal just to keep things simple. So vector v is purely horizontal. Just keep things simple. The vector u is not horizontal, clearly. It's slanted. Can vector u be broken down to horizontal and vertical components? Of course, all vectors can be broken down to horizontal and vertical components. We'll call it W1 and W2. In fact, W1 plus W2 adds up to vector u. Now, we're going to deliberately have vector v go in the same direction as W1. So we want to be going in the same direction. So therefore, those are parallel vectors. Also, W1 is perpendicular to W2 because those are both horizontal and vertical components of the same vector, right? Now, what we call W1, we call it the projection of vector v. So it's basically you're taking vector v and you're projecting the image. It's kind of like, there's an image on my screen, it gets projected, it looks bigger, right? Obviously, it doesn't look that big on my screen, right? But we're projecting it. It's kind of the same thing, right? You're taking a vector and you're going to make it bigger in the same direction. But how are you making it bigger? You're making it bigger based upon this vector. This W1 came from you, right? How's W1 related to you? It's a horizontal component. How do I solve for W1? Wouldn't I do the cosine theta? Isn't cosine theta W1 over Q? So W1 is U times cosine theta. So we know that. So W1 is U cosine theta, as we see right there. Yeah, U cosine theta. And of course, to make it easier to scale up vector V, let's first scale it down to a unit vector. So we scale it down to a unit vector, so it's a magnitude of 1. Because then whatever you multiply to it is going to be its new magnitude, right? So we deliberately scale it down to a magnitude of 1. And then I take the magnitude of W1 or the length of W1, and I multiply. So it's a scalar, right? Because this right here is a scalar. Cosine theta, that's not a vector. The magnitude of U times cosine theta, that's a scalar. That's just a number. And I multiply that to the unit vector. And that is how I create the projection of U onto V. So essentially, you're taking some part of U and you're using that to help you extend going that vector. Why do we have this? It does help for physics. We're going to talk about some physics application in a moment. That's why we have it. If you go through all the math and clean it up, things will cancel. You want to stumble upon this equation here. Because we do know cosine. Where do we get that cosine theta from? Where does that come from? Did that come from over here? Right, that's where cosine theta came from. Because it came from the dot product. So it's just taking what we know originally and or before and just expanding on that knowledge. Okay. So now let's actually look at a word problem. We'll do a problem that's already worked out for us. We'll do one on work, and then we're going to do some examples after that. And hopefully by the time I finish, you guys can work on the homework, which is, well, it's not homework or a break, but just practice problems. The green problems are highlighted in the homework packet. I'll let you guys work on that when we're done, just so you get more practice with this stuff. And of course, I have all the chapter review stuff and final exam review stuff too. Okay. Any questions so far? We're good? Good. It's a little more clear. All right. So physics. Excuse me. Find the force required to keep a car from rolling down the hill. Okay. So for those who are sophomores, I mean, yeah, obviously you're not taking physics right now, but you will soon, right? Or maybe you might, I don't know. Okay. So you have some object sitting on or cart sitting on a ramp. Now, the weight of the cart is 200. Now, if you think about weight, does anyone know the formula for force? What's the formula for force? MA, mass, or how about weight? Mass times gravity. So yeah, I have mass, right? I weigh a certain number of kilograms. What's the acceleration due to gravity for those? I mean, again, if you're sophomores, don't worry. Does anyone know the acceleration due to gravity? 9.8 meters per second squared, right? So if I multiply my mass with my gravity, acceleration due to gravity because I'm on Earth, that's gonna be my weight. And what direction is my weight pointing towards? Down towards the center of the Earth, right? So that's what's happening here. Force is object, regardless of like how it's tilted. Like I could be on the stairs or on some sort of incline or whatever. My force will always be pointing down. What I need to do is be able to break down this force into its components. Now, this is a ramp, right? The ramp has obviously an angle, 30 degrees, right? So we'll say vector V, make it a unit vector. So on map this unit vector to magnitude 1, right? Is this square plus that square is 1. So we'll make it a unit vector. So I'm going to do the projection of F on the V. And why do I want to do that? So I want to know what is the weight that's needed to keep this from slipping, falling down. So I do the dot product of F and V, which is just easy. Divide by that, which of course I know is 1. And then multiply by vector V. So negative 100 cosine 30 sine 30. Wherever that is. That's going to be vector W1. So it's going to the left and down. If you find a magnitude of that, that will be 100. So fine. And that totally makes sense. Because if you think about it, if this is 30 degrees, right? Well, this thing will be right here. 60, yeah. That's 60 degrees. And if that's 60 degrees, wouldn't that be 30 degrees? And using 3690 ratios, the short leg is what fraction of the hypotenuse? Or cosine 30, sorry, sine 30. What's sine 30? So it's 1/2. So it makes sense that this would have magnitude of 100. And that's force required to keep the cart from rolling down the hill. So you'd have to, so that's why ramps sometimes are more advantageous when you're moving it. It's not like if you have movers come to your house or you're moving things to this building, you're not going to lift up like something at 200 pounds. That's going to be kind of crazy. But if you use a ramp, it makes it a little easier because you have that leverage or that advantage. Now, W2, how do I solve for W2? Well, F equals W1 plus W2. So W2 is going to be the vertical component of that force, right? Um, Actually, we call this normal force. So we have tangent lines, we have normal lines. Is there what normal means in terms of like geometry? Yeah, and so it's gonna be perpendicular. So we call this a normal force, and that's used for like friction, that's used for like figuring out like, how to keep things stable. So that's all physics stuff. Again, if you have physics, you're not taking physics. Don't worry, it's not physics class. But sometimes we're interested in knowing that. We're interested in knowing the perpendicular force to the ramp. So this force right here, the force that looks like this, we call it Fn, which stands for normal force. And that is needed sometimes if you have to determine the force due to friction or things like that. So that's why we have these, all these vector things to learn. So solve for W2, well, that's easy. Subtract F with W1. Once you get W2, you can find the perpendicular force. And that's the perpendicular force, 173.2 pounds of force. So that's how I'm working that one out. So that's one example of how we use projection vectors. Okay, another one, work. Now, in physics, work is force times distance. Okay, so force. So for example, I'm doing work to this little podium here because I'm applying force and it's moving. Now, let's say I'm like when I was like food poisoning, I was kind of very weak. I mean, I was able to push something, but or let's just say like Lucas is much probably stronger than me, right? So like let's say I'm trying to push this and Lucas is like trying to really resist it and I can't move it at all. Like I'm like pushing it as much as I can, applying all this force. If I can't move this thing, no work is being done. In order for work to be done, there has to be movement. So like for example, I could push this. How can this wall move? Because there's so much force in this wall. This wall, I can't counteract this force, right? Like this wall is like really strong, right? Like if I try, I don't, I'm not gonna punch it because I'll bloody my hand, but nothing's gonna happen probably, right? So it's kind of this, or the car, right? Like or the tree. The tree fell on my car, right? I couldn't lift it up. There's no way I could lift it up because it's just too heavy. I could put all the force I wanted to. So in order for me to do work, there has to be distance also. Okay. So work equals magnitude of force times distance. So magnitude of force times the vector, the magnitude of PQ. Okay. That's what work is. And this actually does come straight from the physics teachers. They actually have asked us to do this with you guys because they want to make sure you have some exposure to how vectors are used for this calculation. Now, how to use projection for this? In real life, the forces will be at an angle. For example, like let's prove like this, right? They're on a cart. So I'm not pulling the cart like this. And that's an angle. Use the handle, pulling like this, right? But if I break the force down, this force on component, or I project F on the PQ, okay, then I can actually calculate work pretty easily. So I'm trying to compute this. So I'm doing projection of F on the PQ times its magnitude. So work this out. You end up getting
Wait, so you're using a unit vector to find that projection?
correct.
Okay,
Correct.
so that's
Right.
basically, you're just multiplying it by the cosine. You're multiplying the force by the cosine.
Yeah, so what's happening here, if I project F on the PQ, if you think about it, it's really just magnitude of force times cosine theta. So I have this magnitude of force times cosine theta. Now, if I see this here, magnitude of force times magnitude of PQ times cosine theta, I know what cosine theta is. That's from what we've seen earlier, the dot product over these two. And these just cancel. Magnitude of F, magnitude of PQ just cancel. Where are you stuck with? What does that represent? The dot product. So the dot product of F and PQ will give me the work done on that object. The work done on that object. So a dot product can be used to find the work done on an object. So this problem. Well, at this point, we're just going to be using a dot product. What was that? Well, you use a projector to help you understand it. But so here, guys, quiet, please. A force of 50 pounds is exerted at an angle 25 degrees. Determine the work when sliding a desk 15 feet. Okay. So if you think about it, you could just find, I mean, it's a pretty easy calculation. If you do 50 times cosine 25 degrees, that's going to be the force in the x direction. So I call it Fx. I call it the horizontal force. Fy is a vertical force. So you can just do that times 15. That works. If you want to rewrite this as a vector, you could have done this also. 50.
Do we have to rewrite it as a vector?
Not really, because it's kind of a waste of time. Because you could have done this, right? If I rewrote vector F as in vector form, if I wrote force in vector form, right? I'd have this, right? And then what's the distance is pure horizontal, 15 comma 0. So if you think about it, I'm really just multiplying these two together. Well, let's go back to blue. I'm really just multiplying these two together. And of course I could do that as well. But this is 0, so it doesn't matter. It's just going to cancel with this. Or another way you can think about it too is that here's the object. Here's the ground. I have to travel 15 feet. I'm pulling on it like this. My force is being pulled in this direction. But I got to break this down into its horizontal component. How do I do that? I do cosine theta. Cosine theta equals the horizontal component divided by f. Or to solve for the horizontal component, I just multiply it to cosine 25. And we give it as feet pounds because the force is given in pounds and the distance in feet. Now let's look at the next example. And I don't want to move it. But we're going to work this one out to see if we get the same answer. Okay. So this example. Find the work done with that force vector. Is dragged along a line with initial point -3, -5, and terminal point 5, 1. So let's get our distance vector first. What's my distance vector going to be? How do you get that?
5.
Correct, right. And the other one's going to be 1 minus -5. Okay. So now what do I find a dot product of? Where work is equal F dot D, or vector F, which is 1, 6, dot distance vector, or vector D, which is that. If you work it out, you get 8 plus 36, which of course is 44. So what this represents is the work done on this object. I mean, I don't know actually the units. I don't know why I put units. I don't know the units. It's actually unitless. But that's what it tells me.
Wait, can you explain how you got the 5 and the 3?
Yeah, I did terminal minus initial. The terminal point minus the starting point.
Oh. Oh,
Right.
then you got 8.
Correct. Right.
Wait, what? There.
The dot product.
Would that end the force?
Well, sorry.
Would that?
Correct. Right. The last one. And then we could be done for the notes. You guys can work on problems. Okay, vehicle weighing 5,400 pounds is parked on a slope of 10 degrees. So say you're like in a parking garage, sometimes there's a slope, right? So it's kind of like a ramp. We're say in San Francisco. Sometimes that's kind of crazy. A lot of hills. Okay, here's a car. Okay. Crappy looking car. Okay. It weighs 5,400 pounds. So what that means that's gonna be the force. So what you want to do is break it down to its horizontal and vertical components. So you find the horizontal and the vertical components. The force. So assume that the only force to overcome is force due to gravity. Fine. Find the force required to keep the vehicle from rolling down the hill. Then find the perpendicular force. Okay. Actually, it's pretty simple. You don't really have to do this whole projection vector stuff, because you could just say this. If that's 10 degrees, right? Then this is also 10 degrees right here. That's because this right here is the right angle. And that was 80 degrees right here.
I think other angle. Or not.
This just be 80 degrees, right?
Which one?
Wouldn't that be 80 degrees right here? That's 10. Sure.
Because of the X and Y, like where those.
Hold on, that was 30. No, I have it right. Yeah, no, I have it right. Yeah. No, because that's correct. I have it correct.
No, I think you
The drawing
have to draw the triangle the other
Yeah,
way.
it's like,
It's like
making
making.
the normal.
Wait, hold on a sec. Oh, I see what you're saying. Oh, because I drew it.
The legs behind.
Ah, no, you're right. You're right. You're right. You're right. You're right. You're right. Yeah, hold on a sec. Let me redo that. Because I messed that one up pretty royally. Thank you. All right. So you have this. And then
Yeah, it's because that's 10. If the bottom is 10,
Because you're looking for this. Wait one sec. No, no, did I have it right? Hold on. Yeah, should that be? Yeah, because the horizontal force should be much smaller. But what?
What drawing do you have? How is he drawing? You can't just make it. He's drawing it. I like this. No way to put it. I'm going with this. Yeah. Oh, if you're pushing out like this. Let's try it. Yeah.
So you guys are saying it should be this.
Yeah.
So hold on. Wait, you guys saying this is 10 degrees and that's 80 degrees?
Well, I don't know how to explain it to you. I just know that.
Oh, I think I know I did wrong. No, hold on. I got this. Yeah. 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 No, I got it. Here. No, I got it. Yeah, so you guys got like this. So you guys draw like this.
Yeah.
And then this right here would be what? That, but that would be 10 degrees, right? And that would be, so the horizontal force, right, which would be F times sine 10 degrees, right? Yeah, I had that. Did I have that? I'm pretty sure I had that.
It was just the orientation.
Perhaps, yeah. I don't know. Yeah. What do you guys get for your horizontal force then?
937.
Yeah, correct. Right.
Wait, how do we distinguish like pounds being a force versus pounds being like a mass?
We always consider it to be a force.
So like what would so like if like you ask us about like the mass of an object or tell us the mass of what would it be measured?
Oh, kilograms then, but I'm not going to do that because we're not a physics class. So I'll just give you the pound. I'll just give you the force straight up. So
Sorry.
This way like this, would you want to see like a whole vector?
it's up to you.
So there's no gravity, like the acceleration, so like mg, like I don't put in.
Correct. Correct. Yeah, it's not going to be as crazy as you guys do in physics. So correct.
Well,
It's already taken. Well, it's already taken consideration though. It's already taken because it's already taken consideration. And an Fy would be 5,400 times cosine.
And it's just this. I don't know.
At 10 degrees. If I do that, you should get the perpendicular force should be this. Yeah. Okay. I think that pretty much completes everything here. Yep.
Yeah. It would.
wait,
Yeah.
so you also have to multiply the numbers by 9.8.
It's already taken into consideration. Because we're not doing we're not doing mass times gravity. It's pounds, right? It's already a force unit. We already took into consideration. We don't have to do that.
Oh.
It's already taken into consideration. We don't have to worry about that.
Okay.
Yeah. Yeah. So anyhow. Okay, we're all done for today. What I'd like you guys to do for practice, it's not a homework assignment. It's just more just if you want to practice for our test. Do the green problems. Kind of just good extra practice. What was that? Sorry? No, we're done. Yeah, we're all done.
Wait, we're done with semester two, right?
Yep.
Yeah, no.
Yeah. Let me hand out the chapter review packet. Not everything, but just want to get started during break, we can.
And then when we come back, are you gonna give us like practice time?
Yeah.
Okay.
Yes. Oh, I have 10 by.
I haven't missed this thing, how we can manage, you never know.